Let's take a look at a couple more examples of calculating the volume of solids of revolution. So as a reminder, these were the formulas that we derived and discussed on the last video. But what we're going to do when we take a solid of revolution is we're going to determine if the cross-section is a disk. And if it is a disk, then we're going to use one of these two formulas because the area of a disk is pi times the radius squared. As you can see here, pi times the radius squared, pi times the radius squared. Depending on the thickness of the disk, if it's revolved around a horizontal axis, then the thickness is going to be a delta x. If it's revolved around a vertical axis, then the thickness is going to be a delta y when we take a cross-sectional slice. So we'll talk about that when we look at our two examples. But the area of a disk is pi times the radius squared, so then we spend the time to figure out how we find the radius, and we set up our area, our cross-sectional area formula, and then we can integrate across the bounds, whether they're bounds on the x-axis or bounds on the y-axis that the solid lives between. And then the other possibility is that the cross-sectional slice is a washer, essentially a disk with a hole in the middle. So if we have a washer, then we use the area formula pi times the outer radius squared minus the inner radius squared, and we calculate those area formulas and then integrate across the bounds. So that's what we're going to be doing. We're going to follow our steps just like we talked about last time. Draw our region, revolve the region around the specified axis, sketch the solid as best we can, determine what the cross section is, and if it is a thickness of delta x or delta y, set up the area formula and determine those radii or radius if it's a single radius for a disk, and then set up the integral and compute. So let's do it. So let's take a look at this first example. If we want to find the volume of the solid by revolving the region bounded by y equals x cubed, y equals 0, and x equals 1. So our first step when we're doing these is to sketch the region. So let's sketch our region. We're going to be in the first quadrant here. So even though x cubed does, and I'm going to go ahead and just say this is 1 and 1. Really zoom in here so we have a nice little visual. And that's the graph, y equals x cubed. Y equals 0 is the x-axis, so we've got a bound along the x-axis. And x equals 1 is this vertical line right here. Right, so there's x equals 1. And so the region bounded here, and I'm going to highlight it, the region bounded is this little region right in here. So there's the region that we're looking at, and we want to revolve that about the line x equals 1. So we're actually revolving it around one of the bounds. So we're going to revolve it around that vertical line x equals 1. So what would that solid look like? So now let's take that and let's sketch the solid. So the solid, we're going to take that little region, and we're going to revolve it. Actually, you know what? Let's put the y-axis over here because we're revolving around x equals 1. Let's put x equals 1 right about here. This is the line x equals 1. And the region looks something like that, right? We do our best here to get a visual of what this solid is going to look like. And it is three-dimensional. Remember, you think of taking that region and spinning it around, right? And creating that three-dimensional, right? This is like the base. Three-dimensional. It's like coming out of the whiteboard, coming out of the screen at us. So it looks something like this. And when we take a slice, when we take a cross-sectional slice, we cut perpendicular. Remember, we're always going to cut perpendicular to the axis of revolution. So since this is my axis of revolution, think about bringing in your plane cutting knife, and we're going to cut perpendicular to the axis of revolution. So we make a little slice here. You can see the slices. I'll make a couple slices. You can see the slices throughout, and they do change, but you can see those slices, and those slices are discs. So we're going to be working with our formula for a disc. Now, the thickness of each slice, I'm going to go ahead and draw the disc out here so we have some better visual. Pull it out. Here's that axis of revolution coming through, right? And we've got this nice slice of a disc. Now the thickness of the disc is a delta y. So when you come back up here, if you think about that, that thickness right there is a thickness of delta y. And we didn't put our bounds on here, and I didn't even really talk about it, but right here, this ordered pair is 1, 1, because when you plug in 1, x cubed is 1, so that's intersection point is at 1, 1, and this point down here is at the origin, which is 0, 0. So this solid lives between 0 and 1 on the y-axis, and when we're taking those little slices, they are delta y's when we take those little slices to create those discs. So since we're looking for the volume of this solid that lives between 0 and 1 on the y-axis, and its cross-sectional slices are disk, we're going to be setting up our area formula in terms of y. So the area is going to be pi times the radius of these disks squared. So how do we calculate the radius of these disks? So the radius, you can actually calculate the radius from the left or the right of the center, but since our region lives, so if we think about taking a disk, let's do it in red on here. If we think about a disk slice right there, remember where the original region was? It was over here to the left of that axis of revolution. So this is where the radius is. The radius in our picture of the region, it's right there too. It's kind of small, so I'll write radius. In our picture of the region, this is the length that we need to calculate. We need to come up with a formula for this length because obviously this radius and the radius of the disks of those cross sections change as you move up that solid from 0 up to 1. So how do we calculate that radius? Well, that radius is going to be from 1, if you think about calculating that distance, we're going to take the bound on the right, which is 1, and we need to subtract the bound on the left, whatever the value is at that point right there, or at that point there. So how are we going to do that? We need that in terms of y, but our function is written as a function of x. So we just come back up here and we say, wait a second, I wrote this, or when I graphed it, it was given as y equals x cubed, the cubic function, but we could write that as x equals y to the 1/3. Just take the cube root of both sides. So remember, we're just kind of doing a little manipulation there, and our radius ends up being, that radius right here, let's write it up here so we can see it with the visual. That radius ends up being 1 minus y to the 1/3. That's how we're going to calculate the radius at any given y value. So the radius, we'll plug that in. The radius is going to become 1 minus y to the 1/3 squared. And that is the area of any given slice giving us that disk for that solid. And that's actually all we need. We've done the hard work. I'm going to do a little bit of algebra simplification before we go to the integral. But once we have our area formula, we'll be able to integrate it across the bounds from 0 to 1 and calculate the volume. So let's clean that up just a little bit so I don't have to do it in the integral. If I square that, I get 1 minus 2y to the 1/3 plus y to the 2/3. That's my area formula, and now I'm going to put that into the volume. So then the volume of the solid is going to be equal to the integral from 0 to 1 of pi times 1 minus 2y to the 1/3 plus y to the 2/3 dy. And now we're going to just calculate that volume. Let's just go ahead and apply the power rule. So we get pi times y minus 2 times y. We add 1 right there, so we get 4/3. We divide by 4/3, but that's the same as multiplying by 3/4. Plus, we add 1 here as well, so we get 5/3. Dividing by 5/3, that's the same as multiplying by 3/5. And then we evaluate it from 0 to 1, and we've got pi times y minus 3 halves y to the 4 thirds plus 3 fifths y to the 5 thirds, evaluated from 0 to 1. And our answer here, when we do that evaluation, becomes 1 minus 3 halves plus 3 fifths minus 0 when we plug in 0. And so we get pi times, let's find a little common denominator here. What is this? 10 over 10 minus 15 over 10 plus 9 over 10. And we end up with, oh, made a little mistake when I was doing common denominators right there. That shouldn't be 9 over 10. I should write it out too. Trying to do too much in my head here. We were multiplying this guy by 2 over 2, 5 over 5, 10 over 10. This should have been a 6 over 10. And we end up with pi, let's see, there we get 1/10. And so we get pi over 10 units cubed of volume. And we can see, let's get it all on the board. There's the next example. I think we'll do that one on the second video. And there we go. Let me pause the video, move that. And there we go. So again, just following the process, sketch the region, sketch the solid if possible, determine if the cross-section is a washer or a disc, and then determine the radius or radii if you have a washer. Set up your volume by integrating across the bounds that area function that you derived from looking at the disc or the washer.